Hi students, welcome to physics classes. Now we will discuss. In the previous class we have discussed about magnetic field lines. Magnetic field lines. Magnetic field lines we discussed. Now magnetic field lines are starting from the North Pole and ending at South Pole outside the magnet. Now here these field lines are non-uniform magnetic field, means this magnitude of the field strength and the direction of the field lines is changing. Now here it will be more, as going gap will be increases and again gap will be decreases. This is non-uniform magnetic field lines. Non-uniform magnetic field lines. Now here we can see uniform magnetic field lines. These are uniform magnetic field lines. Direction gap between them are equal. Why we are insisting here gap between them? What is the use of gap between them? That we will see end of this class by learning about these topics. Now these field lines, magnetic field lines, uniform magnetic field lines are passing in a direction. Now if you consider any imaginary area perpendicular to the magnetic field lines, imaginary area perpendicular to the magnetic field lines, area A perpendicular to the magnetic field lines. How much area we didn't consider here? One thing we should remember, imaginary area. How much we don't know. Some area, how much we don't know. Now number of field lines are passing this imaginary area. Number of field lines are passing through this imaginary area is known as magnetic flux. Magnetic flux. Magnetic flux. Number of lines passing through this area. Number of lines. Number of magnetic field lines. Number of magnetic field lines are passing through this imaginary area is known as magnetic flux. Magnetic flux is denoted by a letter phi. This is phi, magnetic flux. SI unit of magnetic flux, Weber. SI unit of magnetic flux is Weber. Magnetic flux means number of field lines passing through imaginary area or plane perpendicular to the magnetic field lines. Perpendicular. Field lines are passing like this, area is placed like this. Perpendicular. Perpendicular to the area is perpendicular to the magnetic field lines. Imaginary area. This area we don't know. Suppose if we know this area, number of field lines passing through unit area, number of lines passing through unit area, we know this area, unit area, number of field lines or magnetic flux passing through unit area, number of field lines or magnetic flux passing through unit area perpendicular to the magnetic field lines is known as magnetic flux density. Magnetic flux density. Magnetic flux density. Magnetic flux passing through unit area. Magnetic flux passing through unit area. Magnetic flux density. Magnetic flux density. Now, this magnetic flux density is denoted by letter B, equal to flux passing through unit area pi by A. Pi by A. B, magnetic flux density is equal to magnetic flux by unit area. Area. Pi by A. Now we can write or phi equal to B into A. Phi equal to B into A. Now SI unit of magnetic flux density, SI unit of magnetic flux density, we can say from the formula. Flux units already we know Weber per area units meter square. Weber per meter square. Weber per meter square or Tesla or Tesla. Weber per meter square or Tesla. This magnetic flux density is also known as magnetic field induction. Magnetic flux density is also known as magnetic field induction. Magnetic field induction denoted with letter B. B equal to pi by A or phi equal to BA. Phi means flux equal to magnetic field induction or magnetic flux density into area. Now here we repeatedly said area is perpendicular to the field lines. Only remember these are passing inside, these are outside. So I am drawing with another color. Now if this area perpendicular to the field lines, number of times we said. If it is not perpendicular, for example, if it is like this, area, by making some angle theta with field lines. Some angle theta with field lines. Some angle theta with field lines. Now we can resolve it into two components. Then area becomes A cos theta. A becomes A cos theta. So whenever it is making some angle with field lines, A cos theta, area becomes A cos theta. Then formula B equal to phi by A cos theta. Phi by A cos theta or phi equal to B into A cos theta. Theta is the angle between field lines and area. Theta is the angle between field lines and area. So can we generalize this formula? We can generalize this formula. As we have taken when it is perpendicular, phi equal to BA, B equal to pi by A. Now while coming to area is not perpendicular, by making some angle with the field lines theta, B equal to phi by A cos theta, phi equal to BA cos theta. Should we remember these two formulas? Or can I generalize a formula? Shall we generalize a formula? Yes, we can generalize this formula. This formula can applicable in all the situations. Now we'll generalize this formula. This formula is generalized formula. This is phi equal to ba cos theta is generalized formula we can use in all the situations. When it is perpendicular also we can use. When the area is perpendicular, like this, then it is making zero angle with the field lines. Parallel, no? When area is perpendicular, parallel. So theta equal to 0. Whenever theta equal to 0, phi equal to ba cos theta. When theta equal to 0, cos 0. Cos 0 value 1. So if we apply here phi equal to ba or b equal to phi by a. So this formula phi equal to ba cos theta or b equal to phi by a cos theta is generalized. We can use in any situation. Whatever the angle it is showing, theta. Whenever area is perpendicular, then this is parallel to the field lines. So angle is 0. For example, area is parallel like this. Now it is making 90 degrees with the theta equal to 90 degrees with the field lines. Then what does it mean? Theta equal to 90 degrees, cos 90 equal to 0. Then b into a into 0, phi equal to 0. So no flux is passing through it. No field line is passing through it. Based on this, we can able to determine the strength of the magnetic field. Based on this, we can determine strength of the magnetic field. Now there are more number of lines passing through the area that it is having more field strength. Less lines are passing through area, then we can say it is having less field strength. Now here we see. Now we know whenever we take a bar magnet, we kept in the iron fillings. If we kept the bar magnet in iron fillings, we found more fillings are attracted at the poles. Near the poles. Here also, south pole or north pole. Then we can say more attraction power at north pole and south pole. More attraction power at poles. How? See here. If you consider a particular area, more field lines are passing through it. It is having more field strength. If I consider same area, only 2 are here. Example. Here, how many are there? 1, 2, 3, 4, 5, 6, 7. This one also 8. Here also will be 8. Example. Now here only 2. So whenever it is coming closer, field lines in the area will be increases. Whenever field lines are increases, strength will be more. That's why we are saying magnetic field strength. Magnetic attraction power is more at the poles when compared to the middle. Okay, that is about magnetic flux and flux density. Okay, thank you for watching. Please subscribe.